In this module, we will study the quantum mechanical treatment of a rigid rotator. Now the first question comes, why do we study a rigid rotator? A rigid rotator is studied because it will be a model for a diatomic molecule, and therefore it will give us ultimately rotational energy. The next question is, what does a rigid rotator consist of? Rigid rotator will consist of two point masses which are separated by a fixed distance r. As you can see here in this diagram, the distance of the point mass m1 from the center of the mass is r1, and the distance of the point mass m2 from the center of the mass is r2, and the total distance is r1 plus r2, and that is a fixed distance. It does not change during rotation, and that is why it is called a rigid rotator. Further, it has to be remembered that when rigid rotator is rotating, it will rotate along an axis which is perpendicular to the internuclear bond or internuclear distance, and it passes through the center of the mass. Now, the rigid rotator model in quantum mechanics, as I mentioned it earlier, helps us to predict the rotational energy of a diatomic molecule. Now, the energy which it possesses is the kinetic energy, and the kinetic energy of a rigid rotator is given by, as you can see here, kinetic energy is equal to half I omega square, where I is the moment of inertia of this rigid rotator and omega is the angular velocity. It can also be written in the corresponding form L square upon 2I, where I is the angular momentum of the rigid rotator, and this L is equal to I omega. That means L square will become I square omega square. So that's basically the kinetic energy of a rigid rotator. The moment of inertia I, which appears in this expression as it has been shown in the derivation, it is equal to mu r square, where mu is the reduced mass of the rigid rotator. That means it is equal to m1 m2 upon m1 plus m2, that's the reduced mass, and r is the fixed distance between the 2 point masses. So that is how one can find out the moment of inertia of a rigid rotator. Now, if we have to solve this system quantum mechanically, the first step is to write Schrodinger equation for a rigid rotator. The general expression for the rigid rotator is h cap psi is equal to E psi, and this h cap, as you all know, is made up of two operators, kinetic energy operator and potential energy operator. Kinetic energy operator T cap and potential energy operator V cap. Since in this case we are assuming potential energy to be equal to 0, that means V cap is equal to 0, therefore Hamiltonian will be equal to T cap, that means kinetic energy operator. And kinetic energy, as we have already seen, is equal to L square upon 2I. Therefore, in the operator form, it will become L square cap upon 2I. So that's the Hamiltonian for a rigid rotator. As we will see in subsequent modules also, this angular momentum operator L, as it has been shown here, can be written in the form L square is equal to Lx square plus Ly square plus Lz square, where Lx, Ly and Lz are the components along x, y and z axis, and these components in the operator form are represented in terms of the corresponding position operators and the corresponding linear momentum operators as shown here. Since it is a rigid rotator, it is found that it is more convenient to use polar coordinates in place of Cartesian coordinates, and this can be done using the following expression, which shows the link between the Cartesian coordinates x, y, z and the corresponding polar coordinates r, theta and phi. You can see here that x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. And r square is equal to x square plus y square plus z square. Using these relations, one can transform angular momentum component operators Lx, Ly and Lz into the corresponding polar coordinates. And one can also find out ultimately, and we will show it later on, that L square cap, that means the angular momentum square operator is equal to minus h cross square. H cross is here h upon 2 pi. Then in parentheses we have 1 upon sine theta, delta by delta theta, sine theta, del by del theta, plus 1 upon sine square theta, del 2 by del phi square. So that's basically the angular momentum operator in polar coordinates. Using this expression for the angular momentum operator in polar coordinates, we can substitute it in the corresponding Schrodinger equation about which we talked earlier, and we get the following equation. As you can see here, instead of angular momentum square operator, we are putting its value in polar coordinates, and then we get the ultimate expression as it is shown here. This expression on rearrangement gives us a little modified equation, and ultimately we get equation which is 1 by sine theta del by del theta, sine theta del psi by del theta, plus 1 upon sine square theta del 2 psi upon del phi square, plus 8 pi square I upon h square, then E psi is equal to 0. Here E is the total kinetic energy of the rigid rotator, and I is the moment of inertia about which we have talked earlier. So in polar coordinates, our Schrodinger equation for a rigid rotator looks like as it is shown in equation. Now you must notice from here that here the wave function psi is a function of the two coordinates theta and phi, and these two are independent of each other. Therefore, by using the method of separation of variables, one can say that the wave function psi theta phi will be equal to theta theta and then is phi phi, this product of these two functions. If this form of psi theta phi is substituted in the equation and then rearrangement is done, we get this equation. You can see how it looks. Here then we are making a substitution, 8 pi square I e upon h square is equal to beta, and once we make this substitution, the equation reduces to the following: sin theta del by del theta, sin theta del by del theta, plus beta sin square theta, psi theta phi is equal to minus del square psi theta phi upon del phi square. And if further substitution is done using the method of separation of variables, this equation further simplifies, and you can notice from here that we get equation sin theta by theta del theta sine theta del theta theta upon del theta plus beta sine square theta is equal to minus 1 upon phi phi del 2 phi phi upon del phi square. So here you can see that the left hand side depends only on theta, whereas the right hand side of this equation depends upon phi. So we have been able to achieve the separation of the two variables theta and phi using the method of separation of variables. Now we make a substitution 1 upon phi phi del 2 phi phi upon del phi square is equal to minus m square. We call this to be the phi equation, and m is an integer, and if we make this substitution in the equation and further simplify, we get ultimately one more equation, which is, as it is shown, this is called theta equation. Theta equation is sine theta upon theta theta del by del theta, then sine theta del theta theta upon del theta plus beta sine square theta minus m square is equal to 0. So we have been able to split Schrodinger equation for a rigid rotator, which in terms of polar coordinates had two variables theta and phi, into two equations. One is the phi equation and other is the theta equation. Here I would also like to point out that these two equations which we have got now, theta equation and phi equations, these will be solved separately, and then whatsoever are the solutions of these equations, these will be combined to get the wave function for a rigid rotator as well as the total energy E of a rigid rotator. And all this will be done in the next module. But here, there is one thing which I would like to mention, and that is that what we have learned today, from this one can also solve the Schrodinger equation for a particle in a ring. Suppose there is a particle in a ring, and that particle is, say, of mass m, which is in a ring of radius r, and suppose that ring is in the xy plane. Then the Hamiltonian for such a system will be written as h cap is equal to minus h cross square upon 2m del 2 by del x square plus del 2 by del y square. This will represent the kinetic energy of the particle which is moving in a ring. Since this energy is confined, or this motion is confined to a circle, therefore here also a simpler expression can be obtained by using the polar coordinates. But then here the polar coordinates, since it is in the xy plane, so if we look at our earlier expressions which were linking x, y, z to r, theta and phi, here theta is equal to pi by 2 because it is moving in the xy plane, and therefore we will have only two coordinates x and y, and x will be equal to r cos phi and y will be equal to r sin phi. And please note it here that phi will vary here from 0 to 2 pi because the particle is moving in a ring, and if we start from one point and traverse through the entire circle, the angle traversed would be 2 pi. So the limits here would be 0 to 2 pi. Now if we make these substitutions in our above Hamiltonian, then our expression for del 2 by del x2 plus del 2 by del y2, this reduces in terms of polar coordinates to del 2 by del r2 plus 1 upon r del by del r plus 1 upon r square del 2 by del phi square. So this becomes the expression in terms of r and phi. But you will agree that in this case r is fixed because the particle is moving in a ring of fixed radius r. Since r is fixed, therefore r cannot be a variable. Therefore, the first two terms, which are the derivatives with respect to r, they will vanish, and therefore we will have a new Hamiltonian in polar coordinates, which will be equal to minus h cross square upon 2m 1 upon r square del 2 by del phi square. And if we further make a substitution in terms of the moment of inertia, we get the corresponding expression equal to minus h cross square upon 2i then del 2 by del phi square. So that becomes the Hamiltonian for a particle of mass m moving in a circle in xy plane with a fixed radius r. So once we have written this Schrodinger equation and in terms of polar coordinates, and as we have assumed potential energy to be equal to 0, this equation looks like, as you can see here, that 1 upon psi phi del 2 psi phi upon del phi square is equal to 2ie upon h cross square, but then there will be a negative sign. So, and if we take both expressions to the same side, it becomes a positive side, and the ultimate equation which you get here, you can notice that this equation will be similar to the phi equation which we got earlier in the case of a rigid rotator. So this is a very, very important thing which you must remember, that we have been able to get theta equation and phi equation in the case of a rigid rotator, but in the case of a particle in a ring, we have the phi equation. So how these equations are solved and what will be the resulting solution, these are the things which we will study in our next module. To sum up, in this module, we have studied quantum mechanically a rigid rotator. Rigid rotator has 2 point masses of mass m1 and m2, and these two are separated by the distance r, and that is constant. That's why it is called a rigid rotator. For this rigid rotator, we wrote the Schrodinger equation assuming the potential energy to be 0, and we found that the kinetic energy operator can be written in the form of angular momentum, and we wrote that expression, and then we transform the angular momentum expression, which is in Cartesian coordinates, to the corresponding polar coordinates. And once we transformed it into the polar coordinates, we had the Schrodinger equation for a particle, for a rigid rotator in terms of polar coordinates. Then this Schrodinger equation, using the method of separation of variables, has been split into two equations, theta and phi equations. And now we have these two equations, theta and phi. We will, in the subsequent module, study the solution of these two equations and also see how phi equation also leads to the solution of a particle in a ring.